Okay, today we'll just go through few theorems from Eulerian graph. Yesterday we did one important theorem. Now, this is another important theorem in Eulerian Eulerian graph. Okay, the theorem is a connected graph G has an Euler trail if and only if it has at most two odd vertices. It has at most two odd vertices. So at most two odd vertices means either there are no odd vertices or exactly two odd vertices. So this is the statement. So let's prove this one. So since it is both necessary and sufficient condition because of if and only if, so we'll prove the both direct and the converse part. Let us suppose that G has an Euler trail. We have to prove that it has at most two odd vertices. Look, let us suppose that G has an Euler trail. Then if any V is a vertex of this graph G, okay, then the degree of this vertex is even, because suppose this is the vertex, then there will be one entering vertex and another one is exiting edge. Suppose there is another entering edge, then there will be another exiting. So this vertex, degree of this vertex is always even. Only there are two vertex whose only there are two vertex whose edge is odd. They are the beginning vertex and the end vertex. Only these two vertex will have uh, odd degree, because suppose this is the beginning one, okay, and suppose this is the ending one, it ends over here. So only this vertex and this vertex has got uh, odd degree. Thus the only possible odd vertices are origin and the terminus. Terminus means the end of the trial. And if these two coincide, suppose these two coincide, that means there is a coincide means suppose this is u and this is v. Coincide means suppose u is equals to v, then there is no odd vertices. This graph will have an Euler tour and every vertex is even. Okay, so the possibility is either zero odd vertex or two odd vertex, and this two is this in origin and the terminus. Is that clear? So this is the necessary part. Now if we come to the converse part, if G has at most two odd vertices, then that connected graph G has an Euler trail. Let's prove that one. Converse part. Suppose G is connected and with at most two odd vertices. At most two odd vertices. We have to prove that G has an Euler trail. Let us suppose that at most two odd vertices means no odd vertices or exactly two odd vertices. Let us suppose that it has no odd vertices. Then all the vertices are even. Okay, it has no odd vertices. Then all the vertices has even. Then G is Euler graph, because from the previous yesterday's theorem we proved that if all the vertices are even, then G is Euler. G is a Eulerian graph. Okay, so G has a Euler trail. Is that clear? So first part is true. But if G has two odd vertices, let us suppose that G has two odd vertices. Let us suppose that U and V are that two odd vertices. Okay, and remember that G cannot have just one odd vertices, because in our first 2-3 classes that we have done one theorem that number of odd vertices and even vertices is always equals to even. Okay, is that clear? Because total number of edges is always even, because each vertex gives two at least two number of edges each vertex gives. So total number of vertex is even. That's why uh, total number of odd plus total number of even. Total number of even is also even vertex, and total number of odd will be also even. Okay, that's why G has two odd vertices. G cannot have just one odd vertex. Okay, remember that we have done this theorem. Now let G plus E denote the graph obtained by adding. We just add one edge, G plus E. Adding a new edge joining U and V. We'll join this U and V. Now all the vertex are even. Okay, now all the vertex becomes even. So G plus E, vertex of all the vertices of G plus V even. This implies that G plus E has G plus E is a Euler graph, so it has Euler tool. Okay, G becomes an Euler graph. Is that clear? Let us suppose that Euler tool be C. C equals to V0, E1, V1, E2, dot dot dot, En, Vn. You will get an Euler tool in this way, in this fashion. Okay, and it involves each and every edge of G plus E exactly once. This was the definition of Euler tool. Let us suppose that this E1 BE, this V0 V U, and this V1 B V. Okay, this is U, this is E, and this is V that we have supposed earlier. That's why this Vn will also be equals to U, because we have joined U and V. Okay, so what you will get is that you'll get U, E, and V1 is V. Okay, E2 dot 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 En, and what is Vn? Vn is again U. Okay, so you will get this is on some Euler tool. So this is U, this is V. Okay, and there is E over here. Okay, now just delete this E, so you will get simply Z. Okay, so you just delete E from this tool, you will get V1, E2 dot 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 dot, dot E and V. Just delete this one, so you will get from U to V. What is this? This is an Euler trail, and it involves each and every edge of G, because it was earlier it was Euler tool. Okay, and just you remove one edge, you'll get Euler trail. Is that clear? So a connected graph whose odd vertices there are which has at most two odd vertices has an Euler trail. Is that clear? So this is one theorem. Okay, this is important theorem. Okay, now there was one problem called Königsberg Bridge problem. This is a very old problem. Königsberg Bridge problem. What does this problem says that there are four um, islands. Okay, A, B, C, D. This is A. This side is B. This side is C, and this side is D. Okay, so and there are seven bridges connecting these four island through a river. Okay, let's see. I'll just draw a figure. It is like this. Okay, so the bridges are over here. Okay, this is island A, this is island B. Okay, there are two bridges connecting A and B. There are two bridge connecting A and C. Okay, there are one bridge connecting A and D. There are one bridge connecting C and D, and there are one bridge connecting B and D. So total there are seven bridges. So the problem was, okay, wait. It is said that the townsfolk of Königsberg amused themselves by trying to find a route that crossed each bridge just once. Okay, and they must go to each and every island. Okay, by through that bridge crossing exactly once. Okay, and they were confused whether we can do that or not. Okay, so um, if you draw a figure, a graph showing this Königsberg problem, then it is like this: A to D, A to C, A to B. Okay, A to C. There are two bridges connecting A to C, and there are also two bridges connecting A to B, and there are one bridge connecting C to D, and there are one bridge connecting B to D, and there are one bridge connecting A to D. So look, just check over there that each and every vertex has odd vertices. Yes or no? So A has got 1, 2, 3, 4, 5 vertices. C has got three edges. Sorry, D has got three edges, and B also has got three edges. That means all the vertices are odd vertices. That means according to the theorem that we have learned, we can say that this graph does not contains any Euler trial or Euler tour. Is that clear? If it was like that, that each and every vertex were even vertex, then there must be an Euler tool. Or if at most two of the vertices odd vertex, then we can have that graph has an Euler trail according to the theorem. Okay, but this graph does not contains any even vertex or at most two odd vertex. That's why um, it is not possible to go through um, each and every edge and pass through each and every edge and pass through each and every island. So this was Königsberg bridge problem. So this theorem shows that the Königsberg bridge problem has no Euler trail since every vertex has odd degree. Okay, odd degree. Euler graphs and more generally graphs with Euler trails often appear in books on recreational mathematics or children's puzzle books. Okay, you can see in children's puzzle books that there some diagrams is given and we have to draw without lifting one's pencil from the paper, and also without repeating any lines. You can see that kind of diagrams. Like I'll draw one. You know this diagram. See, in this case, I haven't repeated the lines and I haven't pick up the pen. So this type of diagrams, they are actually Euler trails or Euler tour. Okay, these are the problems from these things. Okay, so I can draw one puzzle over here, and you can also see in the PDF that I have given to you, there are three puzzles given. Okay, so one of the puzzle I'll draw over here. Okay, not like this. I think I didn't repeat any lines and I didn't lift my pen over here. Okay, so this is one kind of puzzles where you can find Euler. So according to the theorems, you can see that each and every vertex are even vertices. Look, this is 2, this is 2, this is 4, this is 4, this is 4. Okay, so each and every vertices are even. That's why we can form a Euler tool in this case and Euler trial in this case. Understood? Okay, there's still two examples given there in that PDF file. You just check it out. In the first second one you can find a Euler trail, but in the third one you can't find a Euler, neither you can find a Euler tool nor you can find a Euler trail, because there are four vertices whose degree is odd. Okay, so this much for the Eulerian graph. There is one Fleury's algorithm, but you don't have in your syllabus, so we're not going through that algorithms and all. Okay, there are some exercises, so try to do those exercises. Okay, uh, just take it over there. If you can't, you can just ask me how to do. Okay, now today we'll start another topic called Hamiltonian graph, and we'll do one two theorems, and we'll finish this chapter. We'll finish this class also. Okay, Hamiltonian graphs. So in this Hamiltonian graph, we have defined this graph in our previous classes also. Hamiltonian. Okay, first we define Hamiltonian path. Okay, you know what is a path. Okay, a Hamiltonian path in a graph G is a path which contains every vertex of G. So in case of Hamiltonian, it contains every vertex. In case of Euler, it contains every edge, but in case of Hamiltonian, it contains every vertex. So there must be some path which contains each and every vertex. Is that clear? So a Hamiltonian path is a graph in G which contains each and every vertex, and that vertex must be used exactly once. Okay, so no vertex of a path is repeated. This means that a Hamiltonian path in G contains every vertex of G once and only once. So this is the definition. You can check in your PDF file. You'll find the definition over there. So I'll just define a Hamilton. Okay, now a Hamiltonian cycle. What is a Hamiltonian cycle? A Hamiltonian cycle or Hamiltonian circuit in a graph G is a cycle which contains every vertex of G exactly once. So it is a cycle in a graph which contains every vertex of G exactly once, except, I can say, except the origin vertex, the vertex from where you start. You This will repeat because you have to go around and you have to come again to that vertex. Is that clear? The begin vertex and the end vertex must be same. So this is the Hamiltonian cycle. So we'll define a graph G is called Hamiltonian. A graph G is called Hamiltonian if it has a Hamiltonian cycle. If that graph contains a Hamiltonian cycle, then we can say that the graph is Hamiltonian. So again, by simply deleting the last edge of a Hamiltonian cycle, we get a Hamiltonian path. Okay, however, a non-Hamiltonian graph may possesses a Hamiltonian path. That is, Hamiltonian path cannot always be used to form Hamiltonian cycles. Okay, okay. Some graphs are given over here. What does it says that Hamiltonian paths cannot always be used to form Hamiltonian cycles. Okay, suppose you have got some Hamiltonian paths. Okay, so we can't use this Hamiltonian path to form Hamiltonian cycles. It is not always possible. Okay, so this is the graph A, B, C, D. So this G1 has no Hamiltonian path. Okay, it has no Hamiltonian path because you can draw a graph touching each and every vertex. Okay, C to A to B. Okay, so you can draw a graph. So there G1 has no Hamiltonian path. Okay, now but if you connect this one, now this has a Hamiltonian path and it has a Hamiltonian path. Okay, but it has no Hamiltonian cycle, so it can go through this and this. Okay, it is a Hamiltonian path, but it has no Hamiltonian cycle. There is no Hamiltonian cycle. If you start from this, you can't end over here. If you start from this, you can't end here. If you start from this, you can't end here. Is that clear? So you this graph has no Hamiltonian cycle. Okay, that's why Hamiltonian path always does not cannot be used to form Hamiltonian cycles. Is that clear? Now you can see this graph. It has Hamiltonian path as well as Hamiltonian cycle. Okay, mm, this. Okay, you again come to the same vertex. That's why it has a Hamiltonian cycle. Is that clear? So this example shows that Hamiltonian path cannot be always used to get Hamiltonian cycles. Okay, these Hamiltonian graphs are named. Okay, I'll clear this one. This is not so important. These Hamiltonian graphs are named after Sir William Hamilton, an Irish mathematician who invented a puzzle called the Icosian game, which he sold for 25 guineas to a games manufacturer in Dublin. The puzzle involved a dodecahedron on which of the 20 vertices are labeled by the name of some capital city in the world. The object of the game was to construct, using the edges of the dodecahedron, a tour of all the cities which visited each city exactly once, beginning and ending at the same city. So he draw a dodecahedron. You know what you mean a dodecahedron? So it is okay. So this dodecahedron has how many uh, vertices? It has got 20 vertices. That's a dodeca. Okay. So what was the puzzle? Each vertex was given the name of the name of a some capital city. Okay. So the puzzle was to visit each and every city exactly once. Okay, we have to visit each and city exactly once in such a way that the beginning and ending city must be same. Okay, so this was the so in this way Hamiltonian graph was formed. Okay, okay, so this was the dodecahedron puzzle. Okay, now you know what you mean a CN. it is a n cycle with n distinct vertices. So this Cn is all is Hamiltonian. It is by default it is Hamiltonian. Okay. Moreover, any Hamiltonian graph, suppose G is one Hamiltonian graph and G dash is a supergraph. Supergraph means by adding in one new edge, okay, between vertices of G. Okay, suppose likewise in this graph dodecahedron you can see that these two edges are not joined, and if you join this vertex, these two vertex over here, this becomes a supergraph of G. Is that clear? So by adding new edges between vertices of G, G dash will also be Hamiltonian. So if G is Hamiltonian, then its supergraph G dash is also Hamiltonian, because any Hamiltonian cycle in G will also be Hamiltonian cycle in Z dash. In particular, you know what is Kn? Kn is called the complete graph on n vertices. Kn, and this Kn is always a Hamiltonian. Remember that. Okay, this Kn, this Cn, they are all Hamiltonian graph. Actually, they are the examples of Hamiltonian graph. Okay, now okay, there are a few definitions. It's called maximal non-Hamiltonian. Maximal non-Hamiltonian graph. A simple graph G is called maximal non-Hamiltonian if it is not Hamiltonian. Okay, so this G is not Hamiltonian, but the addition to it of any edge connecting two non-adjacent vertices. If I add edge E, okay, and that edge E connects two non-adjacent vertices from G, then this is Hamiltonian graph. Okay, so this G is called maximal non-Hamiltonian. So only by adding one edge connecting two non-adjacent vertices of G, you will get Hamiltonian. Then this G is called maximal non-Hamiltonian graph. Is that clear? Okay, I'll give you an example. This graph is maximal non-Hamiltonian graph, because since this is not a Hamiltonian graph, because you can't find a Hamiltonian circuit over here or Hamiltonian cycle over here. Okay, but if you draw this line, you will find a Hamiltonian graph. Now this is a Hamiltonian graph. Okay, so we have just added this edge in this graph. So this graph is a maximal non-Hamiltonian graph. Okay, there are other graphs also. The example of maximal non-Hamiltonian. Okay, I think, okay, I'll draw it. This is maximal non-Hamiltonian graph. DD. Okay, because of this table. Okay, this is again maximal non-Hamiltonian graph, because you can't find a cycle in this case. So okay, wait. From here, if I draw, so you have to draw one edge. If you draw this one edge, I think you'll get a Hamiltonian circuit, right? If you start from there, if you start like this, if you start go this, okay, then you'll get the Hamiltonian circuit, complete Hamiltonian circuit. Okay, so this is a maximal non-Hamiltonian graph. Okay, now we'll just learn one theorem. Okay, this is a used theorem. Okay, it is called Dirac. Okay, this was given by Dirac or Dirac. You can pronounce in your way. That is, if G is simple, with n vertices, n greater than or equal to 3. Okay, n must be greater than or equal to 3, and degree of V is greater than or equal to n by 2. For every vertex V of G, then G is Hamiltonian. So this is the condition for a graph to be Hamiltonian. If G is simple and of with n vertices, and vertices must be greater than or equal to 3, and degree of each vertex must be greater than or equal to n by 2. Suppose degree is 4, suppose number of vertex is 4, then degree must be greater than 2, either 2 or it must be 3, then it will become a Hamiltonian. So this is the condition for being a Hamiltonian. Okay, we suppose that the result is false, that means G is not Hamiltonian. Okay, then but we have got this, n is greater than equal to 3 and degree of V is greater than equal to n by 2. We have got this too, but G is not Hamiltonian graph, it is a non-Hamiltonian graph. Okay, now we draw one super graph of this graph. Okay, so that super graph will also have the same vertex set, because we have only added edge, not vertex. Okay, so has the same vertex set, and also has every vertex with degree at least n by 2, because by adding edge we haven't reduced the degree, we have increased the degree. So its degree will also at least n by 2 newtons. Okay, understood? Because by making a super graph we add age, that means we add degree, so we are not decreasing, reducing degree. That's why degree will remain same for the super graph. Also degree will also be at least n by 2. Okay, so using this G we obtain a contradiction, so we'll arrive to a contradiction. Let's check it out. Okay, first of all, uh, G cannot be Kn, because Kn is always Hamiltonian and G is not Hamiltonian. So there are two non-adjacent vertices U and V. Okay, so we just draw U and V. We join U and V. Since G is not Kn, that's why there is non-adjacent vertices. So we draw an edge and we write G plus UV. So this is a super graph. Okay, so this is the super graph of G obtained by introducing an edge from U to V. Okay, now okay, suppose uh, okay, wait. Okay, now suppose this G. Okay, in G, what we do is that we add edges. we add edges in such a way that G becomes maximal non-Hamiltonian. Understood? So, uh, any proper supergraph of this form is obtained by introducing more edges. So we introduce more edges in Z until there will be a maximal non-Hamiltonian graph G with n vertices and degree of V is always greater than equal to n, because we have added edges. So degree of V will always remain same, greater than or equal to n by 2. Understood? So we introduce edges until G becomes a maximal non-Hamiltonian graph. So G plus UV will become Hamiltonian, because what is the definition of maximum non-Hamiltonian? If you introduce one edge, then that graph will become Hamiltonian. Just with single edge, it will become Hamiltonian. So in this case, G plus UV will become Hamiltonian. Okay, if it is a Hamiltonian, then there must be some Hamiltonian cycle. Let us denote that Hamiltonian cycle by C. Let C be the Hamiltonian cycle, and this C must contains the H UV. Okay, because if it doesn't contain the H UV, then G will become Hamiltonian. Okay, so with this H UV, G is Hamiltonian. That's why C is the Hamiltonian cycle. Clear? So we write C as V1, V2, dot dot dot, Vn, and again V1, because it is a cycle. Okay, so in this case V1 is U, because we have joined UV. Okay, and this Vn is V. Okay, so this V1 is U and this Vn is V. Understood? Because we have joined that U and V. So we take this V1 and Vn as U and V. Okay, now let us define two sets. How we define? One, we define S, another we define T. S are all those edges, a vertex from C. So S is a set of all those vertex Vi from C such that there is an edge from U to Vi plus 1 in G. If there is a edge from U to Vi plus 1, then Vi is the element of S. Okay, so that means suppose there is one edge from U to V4, suppose, then V3 belongs to S. Understood? So in this way the set S is constructed. Again T is constructed in such a way that all Vj belonging to C, then H from U, H from V, so H from V to Vj in G. So if there is an H from V to Vj, okay, you know what is V, you know what is U. U is this starting one, V is your ending one. So if there is an H from V to Vj in Z, then this Vj belongs to T. Okay. Now this Vn does not belongs to T. Why? If Vn belongs to T, then what happens? There will be an edge from V to Vn. And what is Vn? Vn is actually V. So there will be an edge from V to V. That means there is a loop, but G is a simple group. Okay, there is no loop in Z. That's why Vn does not belongs to T. Clear? This is why Vn does not belongs to T. Also, Vn does not belongs to S. Why? If Vn belongs to S, then there is a S from U to Vn plus 1. Okay, but I think we don't have any Vn plus 1 over here. We have got only up to Vn. So that means we have got V1. Okay, and instead of Vn plus 1, we will get V1. V1 means u. So again there will be a loop, which is impossible. Okay, so again this Vn also does not belongs to S. That means Vn does not belongs to S union T. So Vn does not belongs to S union T. Okay, let us suppose that this mode S, mode T and mode S union T. Let us suppose that this denote the number of element in S, T and S union T respectively. Then we can say that S union T is always less than N. Okay, because Vn doesn't belongs to uh, S union T. So only possibility is in S union T there are only V1 to Vn minus 1, not Vn. Okay, the only elements in S union T are V1 to, because in C there are V1 to Vn. Since this Vn doesn't belongs to S union T, then only remaining would belongs to S union T. So it is always strictly less than N. Okay, number of vertex in S is nothing but D of U. Why? Because in S it is those vertices which connects with U. Okay, if so, and the elements of Vs are those Vi when there is a S from U to Vi plus 1. So S means D of U, degree of U, because U connects to Vi plus 1, then you will get the number of elements in S. Is that clear? So similarly, number of elements in T means D of V, because if V connects to Vj, then this Vj belongs to T. That's why degree of V. If degree of V is 1, that means Vj belongs to T. Understood? So this is our final calculation. Now what we do is that suppose Vk is a vertex belonging to both S and T. Let us suppose that Vk belongs to both S and T. Then what happens? You will connect to Vk plus 1 according to the definition. Okay, and V connects to Vk according to the definition of S and T. So what you will get is that U means V1 and V means Vn. Okay, so V1, V2, you'll get Vk, and you'll go to Vn. Okay, again from Vn there is an edge up to Vk, and again it will go to U. Understood? So you'll get like this, up to Vk and Vk to Vn, again Vn to Vk plus 1, again Vn plus 2 U. So this is another Hamiltonian cycle in G. So this is a Hamiltonian cycle in G. Okay, but G has no Hamiltonian cycle. Clear? Understood? And these also connected, but this and this are not connected, because this is connected only in G plus UV. Okay, in G these are not connected. So we can find that there is a Hamiltonian cycle in G, which is a contradiction. Therefore Vk does not belongs to S intersection T. That means S intersection T is phi, is a null set. So S and T are disjoint. Okay, clear? Therefore S union T is equals to S plus T. You know the number of elements in S union T will be equals to number of element in S plus number of element in T minus number of elements in S intersection C. Okay, you know that one. Okay, so in this case S union T is equals to 5. So number of elements in S union T is equals to number of element in S plus number of element in T, which is equals to D of U plus D of V, which is always less than N, because number of element in S union T is always less than N. Okay, but what we have got is degree of u is less than n by 2 and degree of v is also less than greater than equal to n by 2, and this also greater than equal to n by 2. Therefore degree of u plus degree of v is always greater than equal to n. This is given, degree of u plus degree of v is greater than equal to n. But what we got from that assumption that g is not Hamiltonian, we got that degree of u plus degree of v is strictly less than n, which is a contradiction. Okay, so to prove g is Hamiltonian, we have to do all this thing. Okay, so contradiction, hence g is always Hamiltonian. So I want you to just go through these things again, okay, because you will forget all these things, okay, if you don't repeat yourself. So just check this theorem once again by yourself, okay, and try to understand by yourself. And if you can, if you don't understand, you can ask me again which part you're failing to understand, then you can ask me again.